Yes. Yes.
Has anything developed in supervised learning and behavior since?
Yes. Actually, it has.
Oh yeah,
All right, let's get started. So welcome to the second lecture of CS294-112, Deep Reinforcement Learning. And today we're going to talk about the first class of learning algorithms that we'll cover in this course, which are imitation learning algorithms. But before we start, a few logistical notes. So again, make sure if you're an enrolled student, please make sure you sign up for Piazza. That's what we're going to be using for a lot of our announcements. So if you're not signed up for that, you're going to miss a lot of really important stuff, like when your homework is due. So definitely sign up for Piazza if you're an enrolled student. Homework 1 is now out, so if you go on the course website, you can download the handout that tells you how to get started on Homework 1. And actually, in today's lecture, we're going to tell you more or less everything you need to know in order to do Homework 1. So you're welcome to get started on that as soon as you want. And there's a milestone for Homework 1, so the homeworks will be a couple of weeks, but for the first homework, we actually have a milestone, I believe next week on Wednesday. And the point there is just to get you guys started on that so that you can decide whether you should attend the review section, which will be next week on Friday. And Josh will share with you information about when and where that's going to be using Piazza, so you just sign up for that. And the milestone is very simple. The milestone is just like train a network and show us that you've trained a network. And then third point, remember to start forming your final project groups. So we're working right now to put together the final project assignment, some ideas for projects and so on, but you can already start talking to your classmates and trying to find a project group. And groups, again, should be 1 to 3 people. You can have groups larger than 3, but then please check in with me first to make sure that the scope of your project is reasonable. Regarding the waitlist, I've already sent emails to all of you who are, I believe, in the top 40 slots on the wait list. And if you didn't get an email from me, then you are not in the top 40 slots, in which case, very likely, we would not be able to enroll you this semester because we're not going to have the space. So if you did get an email from me, then that email tells you some details about what's going on there. Okay, today's lecture. I'm going to cover the definition of a sequential decision-making problem. I'm going to talk about some definitions like states and observations that are important for us to know. But then I'm going to talk about imitation learning, which is how we can go from essentially supervised learning for decision-making. So algorithms for situations where you do have a human telling you what you should be doing, and you need to learn a behavior from that. I'm going to talk about whether direct imitation, meaning just naively applying a supervised learning algorithm to learn behaviors, works or not, and in which situations it works, and how we can make it work more often. I'm going to talk about a few case studies, basically just discuss some papers that look at deep imitation learning, and then I'll talk about kind of what's missing from imitation learning, and that'll motivate the next lecture for this week. So the goals of today's lecture will be to understand the definitions of the notation for sequential decision-making, and understand basic imitation learning algorithms, which you'll need to do your first homework. And then also understand their strengths and weaknesses. Okay, so let's start with a little bit of terminology and notation. We'll begin with a kind of a supervised learning problem that hopefully all of you are already familiar with. So here, let's say that I want to observe this picture, the picture of the tiger, and I would like to output a label that says what is the category of the object in this picture. And I'm going to use some funny notation here. I'm going to actually start using the reinforcement learning notation for this, which is just a supervised learning problem. So I'm going to call the image O for observation, and I'm going to call the output A for action. So you can think of an image classification system as a system that takes an action, and that action is basically the label. So in this case, the label is a categorical variable. It takes on one of these categories. And the network that actually makes this prediction, this thing in the middle, I'm going to call it pi. Pi for policy. The policy gives us a distribution over actions conditioned on observations. So in the case of an image classification network, you would have a softmax at the top, and that softmax gives you a distribution over those discrete labels. And that network is parameterized with parameters theta, and theta here refers to the weights in the network. So our goal in learning is to find the weights theta that make this network do a good job at whatever it is that it's supposed to be doing. So let's go from this supervised learning setup to a sequential decision-making problem. So the first thing that we'll do is we'll put a bunch of subscripts on everything. We'll put subscript t on everything to denote that these are time steps in a sequential process. So at time step t, you observe the observation O subscript t, and you take the action A subscript t. And the difference between an IID setup that you're all familiar with in supervised learning and a sequential decision-making setup is that the action that you take will actually affect your next observation. So if you see the tiger and you correctly recognize that it's a tiger and you do the appropriate thing, then maybe you won't see the tiger at the next time step, but if you don't recognize that it's a tiger, then you might be in for a bad time. And you can go and you can change your actions to things that maybe make a little bit more sense in this sequential decision-making process. So you could say, okay, I'm still going to have discrete actions, but now instead of outputting labels, I'll maybe output something that, that my agent will do. You can also have continuous actions. So you can say, well, when I see this tiger, I'm going to choose which direction to run. I can run forward, I can run backward. And then instead of having a softmax at the top of my network, maybe I have some sort of continuous distribution. For instance, you might output the mean and the variance of a Gaussian distribution. So in general, the idea is the same. You're just outputting some parameters of a parameterized distribution at the top, and it can be discrete or continuous or hybrid. It could be a mix of both. Okay, so the notation here, we have O, which denotes observation. Observation is what you see. That's what goes into your model. You have A, which is the action. That's the thing that you are actually going to do. That's what your model needs to output. And there's one more thing that we need to introduce to make this definition of sequential decision-making complete, which is a notion of state. So you're going to be learning these policies, and your state we're going to denote with S, and here's the distinction between state and observation. So your policy, by the way, can depend on either observations or states, depending on whether you're fully observed or partially observed. So if I see a scene like this, if I see, in this case, a cheetah chasing after a gazelle, when I see this photograph, what I'm seeing is the pixels, right? So in the computer, it's represented by a really big array of pixel values. That's my observation. Underlying this observation, there's some kind of real physical dynamical system. So there's the position of the cheetah, the position of the gazelle, there are velocities, whatever other physical factors in the world might influence this thing. And that's the state. So the state is sort of the actual configuration of the environment that gives rise to the observation. Now this is not perhaps very specific yet, but let's talk about one of the things that distinguishes states from observations. If I have this picture and an automobile drives in front of the cheetah, as sometimes happens on the savannah, I guess, and the cheetah is no longer visible, the cheetah is still there, right? So the state of the cheetah hasn't changed, but the observation has changed. And in particular, the observation may not always be sufficient to fully infer the state. So if there's this big automobile right in front of the cheetah and I can't tell where it is, I might not be able to figure out the full state, so I have to act on partial information, but the state is still there. So the state sort of fully encapsulates everything I need to know about the world, but everything I need to know about the world may not be directly inferable from a single observation. Mathematically, we can understand the relationships between states and observations by drawing a probabilistic graphical model. So here's the probabilistic graphical model that relates states, observations, and actions. So the states, those are sort of the fundamental thing down here. That's what gives rise to everything. At every time step, the state independently gives rise to an observation. And if you have this kind of policy, the partially observed policy, it's going to act on the observation to figure out the action. So that's the policy up there. And the relationship between states, actions, and next states, this is sometimes referred to as the transition distribution, the transition function, or the dynamics. That tells us how our current state and action will influence the next state. And one of the differences that you might notice already from looking at this probabilistic graphical model is that if you observe the state at time step 2, then the state at time step 3 is conditionally independent from the state at time step 1. That means that if you know the state at a particular time step, you know everything that will happen in the future insofar as that's possible, and you can completely forget the past. So knowing the state at time step t allows you to forget everything about the past and still have just as much knowledge about the future as you had before. That is not the case for observations. So observations are not by themselves conditionally independent in time. So knowing the observation at time step t over here, at time step 2, might not be enough to fully figure out the future because, for example, if there's an automobile in front of the cheetah right here, but it was not in front of the cheetah over here, then maybe knowing this previous observation might actually help you figure out where the cheetah is now. So this is referred to as the Markov property, and we'll talk more about the Markov property in subsequent lectures as well. So if you hear Markov property, what that means is knowing the state at time step t allows you to forget the past, allows you to forget t minus 1, t minus 2, and so on. Okay, a little aside on notation. So in most of this class, unless I slip up and forget, I'm going to use S to denote states and A to denote actions. This kind of notation was popularized with the introduction of dynamic programming by Richard Bellman in the 1950s. And it makes a lot of sense because S is the first letter of the word state in the English language, and A is the first letter for the word action. Those of you that have maybe more of a robotics or control background, or if you see a robotics or control paper, you might notice a slightly different notation where the letter X is used to denote state and U is used to denote action. This kind of notation was popularized in optimal control with work by folks like Lev Panteryagin. This kind of notation also makes sense because X is often the letter that's used to denote an unknown variable, and U is the first letter for the word for action in Russian, upravlение. We'll stick with this for now, but if you see this stuff in a paper, don't get confused. It means exactly the same thing, it's just a different symbol. Okay, so back to sequential decision making. So if we'd like to train our policy to give us distribution over actions conditioned on observations, how can we do that? Well, let's first switch to a problem setting that's maybe a little bit more practical. You know, building robots that run away from tigers is fun, but not really something that has great commercial value. So let's think instead about driving. Let's say that I'd like to make a car drive itself. That seems to be something that's all the rage these days. If I'd like to be able to do that, I can imagine approaching it with a supervised learning approach. I take my favorite image recognition model and I say, okay, well, can I make this thing predict driving actions instead of image labels? So what you can do is you can get a human driver or maybe a couple thousand human drivers, get them to drive their cars with a camera on their car and some mechanism to record their steering and gas and brake commands. And then you basically get this bucket of O's and A's. So they're driving their cars, continuously recording the O's and the A's at every time step at some fixed frequency, and that's your training data, that's your data set. And then you're going to take this data set and you're going to use it to train this network that looks at an image and outputs a distribution over actions, a distribution over steering commands and gas and brake commands. And those commands might be discrete. Maybe you're going to discretize your steering and your gas and brake, or maybe they're continuous. Maybe you output a Gaussian distribution over steering angle and a Gaussian distribution over, let's say, desired speed or something like that, whatever you want. So you're going to take that training data, you're going to send it to your favorite supervised learning algorithm. You know, SGD with momentum works well. You can also use Atom if you're feeling lazy. And then you get your network. And your network, we can call it pi, we can put a subscript theta on it, but really it's just trained with the standard kind of supervised learning algorithms that we all know and love. Okay, that seems like kind of a reasonable idea. Does it work? Well, the theory kind of says no. Does anybody have any ideas why this might not work? Yes?
Because you don't have to inject any control over the system, and it just does everything intuitively?
So the answer is because we don't get to inject any control into the system, and it does everything intuitively. Yeah, so that's kind of part of it, is that the system doesn't get to choose its own action, so it only sees the data that was shown to it by the human, yes?
I think the
correct action to take depends on the state, but we don't observe the state. So it might not be fully determined by the immediate observation.
That can also be part of it, yes. So sometimes the way that the human chose what to do can't be fully determined from just seeing the current image, so maybe the past history of images is relevant, and we'll actually discuss one of the ways to address this. Yes, back there?
You could have like an observation that you never encountered in the imitation training, so maybe you don't have it set action.
Right, so you might see an observation that's just completely outside of your training set, and then your policy will do some crazy thing. And there was a comment back there?
Not enough human data to be a big enough sample.
That's right, or you might just not have enough data and you might not be able to generalize to new situations, right? One of the kind of fundamental theoretical reasons why you might have trouble with this kind of approach, even if you have enough training data, we can explain as following. Let's say that you have a training trajectory, or maybe a bunch of training trajectories. So here, when I show you plots like this, I have one axis that denotes time, and another axis that sort of denotes like a one-dimensional state. So just pretend that the entire state has been projected onto that one line. So you can think of this as a path through time. If you train a policy pi theta, and you then run that policy to try to see if you can reproduce that same trajectory, well, your policy probably was trained pretty well. Like maybe you got a pretty good training error, but it's never really perfect, right? Function approximation is never completely perfect. So when you run this policy, it's going to make like a little tiny mistake as it moves forward. Like maybe over here it made a little mistake and it deviated a little bit from that training trajectory. Now what happened is, when it made that little mistake, it's going to see a state that's a little bit different from the state seen during training. That by itself is not a big deal, right? It'll still make a mistake, but probably a small one. The trouble is that the mistake that it makes in this new state will very likely be a bit bigger than the mistake it made before. Maybe not by much at first, maybe just a little bit bigger, because it will generalize a little bit, but it'll make a slightly bigger mistake. And when it makes that bigger mistake, it'll deviate even more. And the more it deviates, the bigger the mistakes get. So you get this kind of positive feedback where the mistakes get bigger and bigger until eventually the behavior of the policy diverges. So it's really the sequential nature of this process that gives rise to this problem. If it had made just one decision, maybe it would have made a small mistake, but that mistake would have been bounded. But because the data here is not IID, because the action affects the next state, the mistakes can actually compound. And as the mistakes compound, the longer the trajectory is, the more egregious your mistakes will be. So this is kind of the intuition behind the more formal theoretical explanation, which I won't give in this lecture, for why this kind of problem happens. I'll actually give another explanation for this problem that's a little bit more probabilistic in nature later on in the lecture. But it turns out that in practice, if you actually do exactly what I said, the answer to does it work is actually kind of yes. Like it actually, like you can actually do this. Like you can collect a bunch of data, and these are some folks from NVIDIA Research who did this. It wasn't very good at first, but it turns out that similar to one of the comments from you guys, once they collected enough data, it was actually like not bad. I mean, admittedly, this is, like there's some cherry picking going on here, but, enough that they could record these videos and actually show a car driving itself. So something is kind of working, even though perhaps the math tells us that it shouldn't quite work. All right, that's pretty cool. Like you can have a car driving on the highway if you're rather fearless and and have a lot of faith in your work. Cool. So. Why did that work? Well, having enough data, there's a question?
Yeah, question about the videos, is that like single image to action or?
So the results that I showed, to the best of my knowledge, are actually single image to action. There's a little nuance in the training which I'm about to describe. But yes, the policy takes in images, and I believe what it actually outputs is just steering commands and not gas and brake, but I'm not certain about that. And by the way, I don't mean to imply that this is like a good way to make a self-driving car necessarily. Like you should probably have your car at least obey the rules of the road and stop at stoplights. But to each their own. So why did that work? Like what was the thing that addressed this issue of compounding errors? Well, there's a little kind of heuristic that was actually employed in this method that's relatively simple, but in a pretty clever way mitigates this compounding errors problem. So if you look in the paper that these guys published, they have a little diagram of their system. And yeah, there's like a little steering wheel, there's some CNN in there, there's some errors. But the suspicious thing is right here. There's a center camera, left camera, and right camera. Now, what the heck is going on there? Well, the decisions are actually only made at test time using just a forward-facing camera. But at training time, there's a little trick. And the trick is this, that you have a camera facing forward, you record the images from the camera, and you label them with the steering command that the human actually executed. But then you have another camera that's facing to the left that's recording simultaneously. And you label images from that camera with the steering command that the human executed, plus a little turn to the right. And then you have a camera facing to the right, and you label it with the steering command that the human executed, plus a little turn to the left. So if you remember the picture from before with these compounding errors, what that means is that when the car starts drifting off the road in one direction, because it has this additional data of those left-facing or right-facing images that are labeled with the opposite steering angle, it'll have actually seen that data and it'll actually figure out that it needs to compensate. So in this kind of simple environment where all you have to do is output the steering command, you can sort of fake this stabilization property by augmenting the data set just by catching those situations where you're a little to the left, a little to the right, and labeling them with the corresponding command. So can we kind of think about what does this idea really mean in a more general sense, and can it be used to make imitation learning work more often? So this idea is a special case of something called a stabilizing controller. So by showing the network these pictures with deviations on the corresponding correction, it's essentially showing it how to stabilize. It's trying to catch those situations where you're drifting and showing it how it can be fixed. In a more general setting, what this corresponds to is actually giving not just individual training trajectories, but intentionally, that would drift like this, but intentionally trying to construct kind of a distribution over trajectories that are stable, that come from a stabilizing controller. And this has a formal definition in control theory, but the short version is that it's basically a controller that doesn't deviate too much from a particular bounded region. And there's algorithms for constructing these controllers. Hopefully a good human driver would also stabilize their behavior, but a human driver might be a little too good. They might just not make those mistakes that then require the corrections. But if you have the mistakes and corrections, then you're in better shape. One of the things you could do if you have human demonstrations, you can take those human demonstrations and construct a stabilizing controller around them. And we'll actually discuss later on in the course when we talk about optimal control, some algorithms for doing this. So this is one of the ways that you can do it that I'll discuss later in the course is that you can basically take your trajectory distributions, and we'll discuss trajectory distributions later on, and you can try to construct a Gaussian trajectory distribution that has bounded support using algorithms like iterative LQR. So don't worry about these things for now, but we'll cover them later in the course. The main thing I wanted to show you is this little video. This is actually a neural network controlling a little running 3D humanoid, one second, that was trained to imitate a stabilizing controller built around a demonstration obtained from motion capture of a human. Yes, there was a question?
Doesn't this make the system a lot less robust? Because if you deviate too much, then it's never like counter that sort of.
Yeah, so this is a very good question. So how broad this distribution is right here will determine to a large degree its robustness. So in fact, the more noise that you can inject at training time, the more that you can kind of illustrate these mistakes and their corrections, the more robust the resulting policy will be, with the caveat that if you train it on demonstrations that make lots of mistakes, it'll also make the mistakes because that's what it's trained to do. Yeah. Okay, so short version is the little left-right thing is a special case of building a stabilizing controller, and there's actually computational ways to build stabilizing controllers that we'll cover later on in the course. Okay. Now, that was kind of maybe the controls view of imitation learning. There's also a probabilistic view, and this is the one that we'll actually focus on most in today's lecture. So one way of looking at this problem with the drift is that your policy is learning to predict distributions over actions conditional on observations. And it's trained on a particular distribution of observations, P data. So your training trajectory has some distribution of our observations that I'm calling P data. When you actually run that policy, because as the actions affect the observations, it actually sees observations from a different distribution, P pi. And P pi is not the same as P data unless you were actually perfect during training and you see exactly the same initial situations. So the trouble is that P pi is not the same as P data, And that means that you're testing on a different distribution than the one you trained on, which, if you remember from supervised learning, that's not a good thing to do. That's sometimes referred to as domain shift, and in general, supervised learning doesn't guarantee anything if your test distribution is not the same as your training distribution. So can we fix this? Can we somehow make the distribution of observations during training, p data, be equal to the distribution of observations at test time, p pi? And how can we do that? Well, here's a funny idea. Maybe instead of being clever about our policy, instead of being clever about p pi, what if we're more clever about our data distribution? What if instead of just blindly taking this big bucket of data that we got from our human drivers, what if we do something a little different to get a data distribution that's a little bit closer to what the policy would actually see? So this is the idea behind an algorithm called DAGGER, which stands for Dataset Aggregation, and you'll actually be implementing this algorithm in homework 1. And the idea is actually pretty simple. So the goal in DAGGER is to collect training data for training your policy with imitation learning that comes from p pi instead of p data. How do you do that? Well, you do it by running pi. Like, p pi is defined as the observation you see when you run pi, so let's just run pi and let's just collect the observations that it sees. Very simple. So the trouble is that you need labels at those new data points, right? So you don't just need the images, you actually need to know what the corresponding actions should have been. So here's how the DAGGER algorithm works. First, and this is, by the way, a simplified version of DAGGER. There's, the full algorithm is a little more general, but the simplified version works like this. Step 1, do the standard thing. Train your policy pi on your big bucket of data from your human drivers. Step 2, run your policy pi to collect observations. So you run it, leave your camera on, collect your observations, hope that nothing horrible happens, and you get a data set of observations that now come from p pi. Step 3, ask the human to look at all those observations and say what the action there should have been. If this sounds a little bit weird, it's because it kind of is a little weird. Like, you have to have a person like basically watching a movie and saying what the machine should have done, which in some cases is easy, in some cases is actually pretty hard. But that's what you have to do. You have to get your labels. And step 4 is you aggregate, meaning that you merge these two data sets. You take this now labeled data set d pi and your original data set d, and you merge them into your new complete data set d. And then you repeat. You go to step 1. And as you keep doing this, eventually more and more of your data set d contains on-policy data, contains data from p pi, and the algorithm can actually be shown to converge and have bounded regret. So you will eventually get a policy that does a good job of mimicking the expert at the observations that the policy actually sees rather than merely the observations that the expert showed you. So in particular, the guarantee that you get from this algorithm is that your error against the expert at the observations from p pi will be bounded. All right. Does anybody have any questions about this algorithm? You'll be implementing this for your homework, so if anything here is not clear, yes?
How do you know when your convergence satisfies?
So I don't remember what convergence test they had in the paper, but one simple thing you can do is you can look at whether or not your network is changing anymore. Because if your network stops changing, that means that your data set is not changing either. Any other questions? All right. Yes?
What actions does it take while it's generating the data set?
So when it's generating the data set, it's running the policy. So that means that the actions need to be actually sampled from pi. And this is very important because you need to actually observe the observations that you would see if you were running the policy. So you need to actually run the policy for that. Yes?
You said it's bounded with this algorithm, but maybe the bound is not sufficient.
So the bound is in terms of training error. So if you can bound your training error, which is a fairly strong assumption in some cases, if you can bound the training error, then you can bound the error on the data distribution from the policy. So this is sort of analogous to the standard kind of supervised learning result, where if you train and test on the same distribution, you get error that's representative, like if you have enough training data. Same thing, except that now your distribution is going to be p pi. Yes?
Is there an issue with efficiency here, especially in the case of driving? You can't just be running these massive optimization algorithms.
Well, yeah. So this is where we get into kind of the details of how you would actually set up this training, right? So depending on how this whole cycle is implemented, there's a range of decisions to be made. Like when you run step 2, do you collect like a small data set or do you collect a gigantic data set? You could, for example, run, if this is a car, you could run it for like 5 minutes, ask a person to label those 5 minutes, and immediately retrain your network, or you can run it for a year and then ask a person to relabel that, right? So all those are decisions that need to be made to really kind of optimize this pipeline, and you guys will get to experiment with Dagger a little bit in your homework assignment, and these are things that you can play around with to see, are you better off collecting and relabeling more often? Are you better off doing it in batch? Are you better off warm starting or cold starting the network in step 1? So should you initialize the weights from your previous solution, or should you initialize them from scratch, and so on. So these are all things that depend very much on the particulars of your problem. Any other questions? Okay. So here's an example of this algorithm called Dagger. This is a first-person view from a drone, and this drone is navigating around trees. And the drone was trained using Dagger. So first there was a little training set that was demonstrated to initialize the network, and then it flew itself around these trees, and a person went in after the fact, relabeled those images with the appropriate labels, and then the system was retrained and it repeated the process. And you can see it kind of flies around trees here. Okay. What are some of the problems with this approach? Well, any guesses? Any ideas about what some of the things that are a little difficult might be? Yes?
It doesn't use any of the previous observations. It only uses OT rather than OT.
That's right, yeah. So the policy that you get, the way I describe it, is actually reactive, so it's only looking at the current observation. And I'll talk later about some of the ways we can address that. Any other ideas? Yes?
You're asking for a lot of humans' time.
Yeah, so we're asking for a lot of human labeling time. And in particular, it's this third step that's kind of problematic. Not only is it a lot of labeling time, it's actually a little trickier in some situations than just getting raw demonstration data. So if you just want data of somebody driving, you just put them behind the wheel and they'll drive the car. But here you specifically need them to label the particular observations that you collected. And people aren't necessarily going to be very good at that in all cases. So could we make it work without more data? Can we make imitation learning succeed in situations where you don't want to necessarily have people go and retroactively relabel things? The short answer is that in the general case, no, we can't. But in practice, we very often can. And this is, by the way, a story that we'll see time and time again in deep reinforcement learning, that oftentimes sort of the theoretical answer is no in general, but if with enough effort and enough determination, you can kind of get things to work in practice. So Dagger addresses the problem of distributional drift, if we want to call this kind of by an informal word, meaning that as you make mistakes, your errors compound and you get into more and more unlikely situations, and if you didn't have that in your training set, then you're in trouble. So that's this picture. So what if our model was so good that it didn't drift? Like, what if it was so good that it just never made mistakes that were big enough for errors to compound? This is a little far-fetched, and in general, it's you can't really show that you can build a model that does this, but in practice, oftentimes, you can actually build models where the drift is small enough that naive imitation learning does work. But there are often a couple of tricks that are very helpful for making this work. So you need to mimic the expert behavior very accurately. And in order to do that, you need to understand some of the reasons why it might be hard sometimes to mimic the expert. And if you can understand those reasons, then you can try to address them and build networks that actually do a very good job of fitting the expert data, but don't overfit, and therefore don't make mistakes that very frequently result in this compounding errors. You can't completely remove the compounding errors problem, but you can mitigate it to some degree in some situations and actually be able to get standard naive behavior cloning to work pretty well. By the way, behavior cloning is a term that's sometimes used to refer to the naive approach of simply taking that big bucket of data and training on it with supervised learning. All right, so let's try to understand why we might sometimes fail to fit the expert. There are kind of two reasons that I'm going to discuss in this lecture, although there are likely others as well, but two big reasons for which we have reasonable solutions. One is that the expert might not be Markovian. So what that means is that the expert's behavior might not depend entirely on the current thing that you're seeing. And the second reason is that the behavior might be multimodal. And we'll get into what both of these mean and how we might address them. So let's start with a non-Markovian behavior. So, and some of the comments that you guys mentioned actually alluded to this already. So you'll notice that the policy that I've been working with so far depends only on the current observation. So if we see the same thing twice, we do the same thing twice, regardless of what happened before. That's not an unreasonable assumption in some cases. In an environment that's fully observed, which means that the state can be obtained from a single observation, you can actually show that there exists a policy that is optimal, meaning as good as any other policy, that is Markovian, meaning that it only depends on the current state. In partially observed settings, where you have an observation and the state cannot be perfectly inferred from the current observation, this in general is not the case. But in fully observed settings, it is. That said, just because the policy is optimal doesn't mean that's what the human is demonstrating. So even if the optimal policy might be Markovian, the human might not demonstrate that policy to you. They might demonstrate something a little worse. So in general, the statement that if we see the same thing twice, we do the same thing twice, it's often very unnatural for human demonstrators. Like, you know, if you're driving a car and you have like a near miss, like maybe you have to like swerve out of the way to avoid somebody, maybe you'll be driving a little bit differently for a little while, and maybe it's hard to understand why you did that without understanding what happened in the past. Or, you know, if you see a sign that says like, you know, children at play or something, maybe you'll slow down even when the sign is no longer visible, and it's hard for the system to figure that out if it's just seeing the current image. So there are all these situations that might happen where the past does affect your behavior, whether it's optimal or not. So what we would really like to do, if we want to address this problem, is to have a policy that somehow considers everything that happened in the past, not just the single current image. So if the behavior depends on all the past observations, then we don't have to worry about this. Then we can actually mimic even behavior that is not Markovian. So how can we use the whole history? Well, we have our neural network. In this case, if you're processing images, maybe it's a convnet that takes in an image and outputs a distribution over actions. So let's have it take in a whole bunch of images. Let's have it take in all the images you've seen in the past. Maybe that's not a very good idea, because now your input might not even be a fixed size. And if you do pick a fixed size input, maybe it's very large, so you might have too many weights. So this is like a reasonable place to start, but maybe not such a good idea in practice, especially if you want very long histories. So what you can do instead, and this is the solution that's kind of the most popular for these kinds of situations, is to use a recurrent network to represent your policy. So this is a network where you process each image in your history through, let's say, some convnet or some other kind of shared layers. So at every time step, these weights are all shared. And then the output of this thing is fed to a recurrent neural network that actually propagates information forward in time. And it's trained in the same way as before, so it's trained to maximize the probability of the actions observed in the training data, so it'll figure out how to use these weights to do sensible things. The particular design of these RNN cells is a little delicate, so you have to be a bit careful there. One thing that works as a reasonable default is to use an LSTM cell, so this is a kind of a particular design for a recurrent neural network that is a little bit better at propagating gradients far into the past. We won't talk too much about architectures in this course, but if you're interested in understanding these designs a little bit better, if you look up LSTMs, you can get a bit of an idea of how to build these things. But this is the high-level kind of principle. Any questions about this? Yes?
So does the storing the history, like how does that relate to like the development updates? Is that like the equivalent in?
So for now, we're actually not doing anything with Bellman updates or dynamic programming. Right now, this is just for mimicking an expert. So the reason that I'm talking about it now before I get into the RL stuff is mainly because I want to talk for now about policy designs. And you can use these policies with reinforcement learning and Bellman updates, as we'll learn later in the course. But for now, we're just talking about supervised learning. Any other questions? Yes?
So when you talk about the states in the Markovian setting, does it only include the state of the environment, or does it also include the intention of the human, let's say where I want to drive, so that you don't always turn left at the same intersection?
Yeah, so the formal definition of state is actually given by that graphical model. It's the thing that if you know it, you can decouple from the future from the past. Now in practice, if you're modeling a decision-making problem, if you're, depending on how you're modeling it, you might actually design the state manually, or you might learn it or something like that. Whether or not the state includes things like intentions of agents depends on how you want to model it. So if there's something in the environment that is not part of your state and you fail to model it, then the way that it's captured by the resulting model is through stochasticity. So it says that if I don't know why something happened, like maybe the weight of an object is not part of the state, but objects actually have different weight, then I'll simply assume that whatever variability I observe is due to stochastic dynamics. And this is typically a modeling decision. All right. So that was how we could handle non-Markovian behavior if we're doing imitation learning. Now let's talk about multimodal behavior. So multimodal means this. Let's say that I'd like to show you how I can avoid a tree. Maybe I'm flying that drone in the video that I showed before, and I'm avoiding the tree. Well, I can avoid the tree by going left, or I can avoid the tree by going right. But it's a very bad idea to try to do the average of these two things. So if I have discrete actions, there's actually no problem here. If I have discrete actions, maybe I have an action for going left, an action for going straight, and an action for going right, I'll just output this as my distribution. High probability left, high probability right, and low probability forward. But if I have continuous actions, or if I have very high dimensional discrete actions, this kind of stuff starts getting pretty messy. So if I have, for example, continuous actions, maybe I'm going to output the parameters of a Gaussian distribution, but now if half the time the human went left and half the time they went right, and I fit a unimodal distribution like a Gaussian to it, I will actually get exactly the bad thing, which is going direct, which is this thing basically, right? The thing that you don't want to do. So how can we address this? And this turns out, by the way, to be, this is kind of a special case of a bigger problem that happens very often in imitation learning, which is that people are kind of inconsistent. Like, people don't actually do the same thing twice, and not just because it depends on the history, but just because there's like other reasons that cause them to do different things. So they will drive left or right around the tree for seemingly arbitrary reasons, even when it's not optimal. So this kind of problem this is sort of an extreme case of it, but it happens very often in imitation learning. So what are some ways we can address it? Well, we have a few options, and I'll talk about three particular options that are quite popular, but there's others as well. One is if you have continuous actions, you can output a mixture of Gaussians instead of a single Gaussian, or some other multimodal parameterized distribution. You can use what's called an implicit density model, which is a somewhat fancier solution, but it's very general, very powerful. And you can use what's called autoregressive discretization. So let's talk about each of these in turn. The mixture of Gaussians, that's exactly what it sounds like. So instead of having your network output the parameters of a unimodal distribution like a Gaussian, you have it output the parameters of a multimodal distribution like a mixture of Gaussians. So you might, for example, say that your probability of an action is a weighted sum of a bunch of Gaussians, and you're going to output the weights, the means, and the covariances of all these different Gaussians, and then you can represent multiple modes. The nice thing about this is that it's simple. It's conceptually simple. It's also implementation-wise relatively simple. The downside is that you have to pick the number of modes. So it's better than a single mode, but up to a point. So if you have 4 modes and the person actually exhibited 10 modes, maybe you're still in trouble. Let's talk about implicit density models. Implicit density models are very, very powerful models for representing any probability distribution, and they work like this. You're going to output something simple, like you're still going to output, for example, a single Gaussian or some other relatively simple distribution, but now you're going to actually input not just the image, but some kind of noise into this network. So maybe you just sample from a spherical Gaussian of some fixed dimensionality. And now your network gets to transform the image and this noise into the output. And because the network can learn any nonlinear function of the input, it can actually transform these unimodal noise samples into multimodal outputs. So it's called implicit because the stochasticity sort of enters as input. In fact, out here, you don't even need to output a Gaussian. You could just output a single value. And it's still modeling a distribution because of this noise down here. The main trouble with implicit density models is that they're a lot harder to train. So when we do supervised learning, what we're really doing is maximum likelihood, and maximum likelihood requires differentiating the log probability of a sample. And doing that with implicit density models is quite a bit harder. So I won't talk about that today, but if you're interested in learning about this, I would recommend looking up things like variational autoencoders, generative adversarial networks, and Stein variational gradient descent, which are just 3 examples of methods that try to train these implicit density models. So the good thing is that they're extremely powerful. They can represent virtually any distribution. The downside is that they're both conceptually and practically more complex to implement. The algorithms that can be used to train them are all approximate inference algorithms, so they're not exact, like for the Gaussian mixture models. but you get a pretty powerful model in the end. All right. Number 3, let's talk about autoregressive discretization. So if you have continuous actions, I mentioned before that if you have discrete actions, there's no problem. So if you have continuous actions, well, you could discretize them, right? You could basically tile them on a grid and then turn them into discrete actions. Which is fine if you have like a 2-dimensional action, even if a 3-dimensional action, but if it's like 5, 10, 20-dimensional, then discretization gets really impractical because it goes up exponentially with the number of dimensions. How many discrete actions you need goes up exponentially. This is sometimes referred to as the curse of dimensionality, which we'll talk about later on as well when we talk about RL algorithms. But it turns out that if you want to train your neural network to output discretized actions, there's a little trick you can do to avoid discretizing all the dimensions jointly. What you do is this. You first discretize the first dimension. So let's say you have 3 dimensions in your action. You discretize the first dimension, and you output a softmax over that dimension. And then you sample from that softmax. That gives you the value for the first dimension. And then you feed that sample into another network. And that other network might also take in the image or the hidden state from here, but it has to take in the discrete sample. And that network is going to produce a softmax over the second dimension. And then you sample from that, and you get dimension 2, and so on and so on. So the nice thing about this approach is that the second part of the network that outputs dimension 2, it's conditional on the sample for dimension 1. So this is learning the probability of dimension 1, and this is learning probability of dimension 2 given dimension 1. So you can still represent any joint distribution over these discretized actions, but you only ever have to discretize 1 dimension at a time. And then when you train this thing, of course, during training you don't sample. During training you actually give it the true values of each dimension. So training is still very easy, just standard supervised learning. And then at test time you have to do this funny thing where you sample, feed it into the network, and then repeat. Yes?
So can you just elaborate on that a little bit? Because if we were plugging in a value before, then how do we now plug in a distribution to the input of the next network?
So that's the thing, that you sample first. So you don't plug in a distribution, you actually plug in the value. So here you have a distribution over a discrete value for the first dimension. Maybe you can take on one of 3 values. You sample based on that distribution, and you get one of those 3 values. And you just plug that into the next layer.
But then during training?
And during training, you don't actually do the sampling. What you plug in is the true value for that dimension. So training is actually very easy. Training, you know what the action was for every dimension, so you just plug that right in. So it's actually exactly the simple and obvious thing. Does anybody have any other questions about this? Yes?
Do you include all previous dimension values for subsequent dimensions?
Yeah, so in general, if you want to be able to model the full joint, then technically every single dimension needs to get as input everything that came before it. Because you want the probability of dimension 3 given 2 and 1 and so on. If you know something about independent structure in your actions, like maybe you know something that you know about the problem tells you that some actions are independent of others, then you can exploit that. But in general, you have to feed everything. There was a question back there first.
So do the different layers share the weights, or?
No. So in general, in this case, the different layers would not share weights. I think you were next.
Same question.
Okay. Yes?
You really briefly mentioned very high dimensional discrete outputs are also a problem for having this kind of multimodal expert.
Yeah, so you can use the same autoregressive trick if you have just many discrete actions. So if you have, let's say, discrete left, discrete right, discrete step on the gas, step on the brake, right? The full action space actually involves the Cartesian product of all of those. So you can step on the gas and turn left, step on the gas and turn right, and so on. So in that situation, even if the actions are inherently discrete, you might still benefit from this kind of architecture because you don't have to have the full joint softmax over everything. Any other questions? Yes?
Do people use RNNs for the autoregressive discretization?
Yeah, so this is the question before about weight sharing. By default, you don't. In some cases, you could if something about the structure of the actions sort of naturally lends itself to that. So, like, I don't think there's any reason a priori to believe that stepping on the brake should share the same weights as turning the steering wheel. But sometimes your actions might actually be sort of structurally similar, in which case it might make sense to share those weights and use an RNN. Yeah. Okay. Any questions about the 1 and 2, about the mixture of Gaussians or the implicit density model? All right. So let's recap what we learned about imitation learning. So imitation learning is often but not always insufficient by itself. So because of the distribution mismatch problem or this compounding errors problem, but sometimes it does work well. So for example, it might work well if you have hacks like the left-right camera trick, which is a special case of a stabilizing controller. It might work well if you actually are lucky enough to get samples from some stable trajectory distribution. Maybe it was constructed computationally using a controller around a human demonstration. You can add more on policy data, for example, using Dagger, which you guys will try for your homework. Or you just use better models that just fit the data more accurately so that this drift is less of a problem. The problem never completely goes away, but it might be less of a problem in your particular use case. So as like a general kind of point, if you do have a problem that you're trying to solve with imitation learning, and you'll probably discover this on your homework too, like just behavior cloning is actually often pretty good. Can't promise that it'll work, but it's definitely worth a shot. And if it doesn't quite work, things like multimodal distributions or RNN-based policies might be good to try before jumping to more heavyweight solutions. All right, let's take like a little maybe 3-minute break, and then I'll talk about some case studies of research papers. So we'll come back at 11:32.
What exactly is a policy?
So a policy is something that gives you a distribution over actions, condition on either states or observations. Yeah. Sure.
This is, maybe I should say the logistical one for Piazza, but for when you have the pi data distribution and the pi data distribution problems that were diverging, can we just optimize that divergence directly? And
you can. The trouble is that that's an objective on your observations rather than your actions. So you can do that using RL, but it's hard to do that with imitation learning. So this is something that we might cover actually much later in the course when we talk about more advanced imitation learning topics. You can actually combine demonstrations with RL and actually use reinforcement learning to track demonstrations, and then you can address that problem. Yeah, so this will be covered like maybe halfway through the course.
How many people do you think from the waitlist will still be added to the class? I'm an undergrad.
So if you received an email from me, the email explains it, and if you didn't, then that means that you are 41 or later on the wait list, which probably means that we won't be able to send you a code. I mean, it depends on how many people drop, but usually it's less than a third of the class.
What made us still able to be on the first spots in the wait list?
We should talk about that afterwards.
That's a good question. So what's the setup for the supervised learning problem? Like what's the label in that case for imitation learning?
The action.
The label is the action based on what the human driver did.
Yep.
So if your observations are things that the human driver doesn't have a label for, that's why you augment the data set? Or
Right. So the reason for the augmentation of the data set is that when the policy drives itself, it might see things that are different from anything that was shown in the data. Not just different in the sense that they're different images, but it might come from a different distribution. So if you swerve off the road and go into like the forest, nothing in the data prepares you for that. So that's what the augmentation is for, is to ask the human, what would you have done in this situation?
Okay, and the reason that the errors can augment themselves is because the human would have taken a slightly different action because
yeah, the human would have basically corrected the mistake, but because you never even saw that mistake, you don't know how to correct it. So that's why the left-right camera addresses this, because the left-right camera basically fakes mistakes.
I'm just wondering about when I should expect it to receive the code.
Did you receive an email from me?
Yes.
So it depends on when other students drop the class. So we're guessing how many people will drop, right? So as students drop, we send codes.
Okay. I'm definitely around like 20 on the wait list.
Yeah, so there's not much more that we can kind of guarantee, because it just depends on who drops the class or not. All right, could everybody be seated? We're going to resume. All right, so for the second half of the lecture, this is going to be a little bit more relaxed. I'm just going to tell you about some work that has used imitation learning and some results in the literature, and also maybe show you some nice videos. So for the first case study I'm going to discuss, this one is actually kind of similar to the NVIDIA paper in a lot of ways. So this is a paper called The Machine Learning Approach to Visual Perception of Forest Trails for Mobile Robots. And let's see if I can just play the video here. So the objective in this paper was to make a quadrotor fly down a forest trail. I'm not sure why you need a quadrotor to fly down a forest trail, because it can fly, but maybe you need it to like follow a hiker around or something like that. So visually, this is actually quite a challenging problem, because you have to look at this picture of this really messy forest trail and figure out like where's the trail and where are the trees so that you stay on the trail. And what these guys wanted to do was train this quadrotor to follow forest trails using imitation learning. So the robot is going to perceive the trail using an onboard RGB camera. And these are some pictures of the trail being perceived. See if you can guess where the trail is here. This is, I believe, in like rural Switzerland, so it's very picturesque. And here's how they solve the problem. So they're going to do the left, right, center thing. So it outputs one of 3 discrete actions, going left, going straight, or going right. And the way that they collect training data is really quite amazing. So flying a quadrotor for a really long time is kind of tough. Like it runs out of batteries, you have to recharge it and so on. So they're going to train you'll see in a second, they're going to train their classifier. Yeah, it's a ConvNet, it has lots of layers. The more layers, the better, obviously. And lots of neurons and many, many connections. And in the end, there's just 3 actions. And here's, that's what training looks like. Sorry. It's been a while since I saw this video. Okay, so this is the part that's really, really cool. Can you guess how they collected their training data? This is amazing. So this is the human walking around with 3 GoPros on their head, and then all they do is they just say this one should be labeled as right, this one should be labeled as straight, and this one should be labeled as left. Very, very simple. There isn't even a quadrotor involved during training, and it ends up actually like working pretty well. Like it can actually fly along forest trails. So this is, I think this is actually super cool, and like anybody could grab some cameras and go and do this. So yeah, that's what it looks like. Well, I guess not everybody. You have to be prepared to like handle a little bit of embarrassment maybe. But yeah, so that's very similar principle as for why this works as the NVIDIA driving, and then they have some analysis in the paper of confusion matrices and so on. So that's imitation learning, actually without even having a person operating a robot. Okay, the next, well, does anyone have any questions about that first case study? Yes?
So you mentioned term right, but what if that right motion was too much and it overshoots and it gets unstable?
Yeah, so you're really relying on the diversity of training data to rescue you from this. So if you really do go too far and you see something that's completely out of distribution, then you're in trouble. But if you remember from that video, like the person's head is shaking all over the place. So hopefully they looked around enough that you got a decent coverage. Yes?
How robust is it to height?
That I don't know. That you have to look in the paper. I don't remember. Okay. So let's talk about another case study. This one is actually going to be using the Dagger algorithm. And in this paper, they're trying to do something a little bit more than just avoiding trees that I showed before. They're actually trying to deal with domain shift, meaning there's training data obtained in different domains, for example, in the summer or in the winter, or on different quadrotors. And they're trying to have the system work well even in the presence of this domain shift. So they're going to be using Dagger. That's the algorithm that I discussed before. And the way that they do step 3, asking the human for an action, this part is a little tricky for them, right? Because this is a high-speed vehicle. You can't just have a person sitting there with a joystick trying to pilot it if it's not actually being piloted, if it's just playing back a movie, because the person relies on feedback. So this is a little hard to label for Dagger. What they did is they kind of set up a little interface that's a little bit more intuitive, where they actually have a person look at a picture and they just draw a line in that picture and they compute what should the steering command be in order to get the quadrotor to fly in the direction of that line. So they had to do a little bit of manual engineering to set up a user interface to make step 3 kind of tractable for humans. And then what they're going to do, let's see if I okay. So what they're going to do is they're going to train a convolutional neural network that will look at pictures and is going to output the actions for the quadrotor. And if they have different domains, like let's say they have some data from summer and some data from winter, and maybe the data from winter, there's a very small amount of data, right? if they'd like to make it fly successfully in the winter, what they're going to do is they're going to train a single network on both. So maybe this part of the network is trained for winter and this for summer, and the weights between the red and the green are shared. Now, this doesn't by itself allow you to fly successfully in the winter because the network might just memorize it, like in winter do this and in summer do that, and overfit to the small amount of winter data. So what they do in addition to that is they introduce what's called adversarial domain adaptation, which is a loss that says whatever features you have in these upper layers, they should look statistically similar between the two domains. Meaning that if you just look at the features in the upper layers of the network without looking at the picture, you shouldn't be able to tell which domain you're in. Because the hypothesis underlying this is that flying in the summer is the same as flying in the winter, so anything that's specific to winter or summer should be sort of removed from the network. So this adversarial domain adaptation allows them to build a network using small amounts of data from the winter domain, large amounts from the summer domain. It might actually be vice versa, I don't remember, and have it actually generalize successfully. And then the kind of combinations of domains they consider are, I think it's summer and winter, a forest in Switzerland and a forest in Pittsburgh, and then two different quadrotors. So they consider these different conditions, and then they show that, yes, indeed, if you incorporate domain adaptation, you do actually get generalization even with small amounts of data from the target domain. So this is kind of a neat combination of Dagger to handle the domain shift between training and test, and also this domain adaptation to handle the domain shift between the two domains, between the summer and the winter. Any questions about this work? Yes?
Does creating an autoencoder also help with the domain shift?
Does training an autoencoder also help with the domain shift? So autoencoders can be used to actually regularize representations, and I'll actually talk about that in a subsequent paper. They don't by themselves inherently reduce issues with domain shift in particular, but they can reduce some overfitting problems. Any other questions? Yes? I think that in this paper what they do is they have multiple fully connected layers and they put the loss on all of the fully connected layers. Conceptually, if you have a domain adaptation loss, in principle it's enough to just put it on one layer, because basically once you bottleneck the information through that, everything afterwards, like if the information about the domain goes away, it can't reappear in a later layer because it's gone. They found it beneficial to put this on multiple layers. Okay. So the next case study I'm going to talk about is actually for robotic manipulation. So what these guys wanted to do is they wanted to use a robotic arm to move some objects around, and they collected demonstrations actually using a video game controller in a simulator. And what these guys did is that they had the recurrent neural network policy to deal with the non-Markovian actions, which turned out to be a big problem for them here, and they used a mixture of Gaussians as the output to do multimodality. So those are two of the ideas that we talked about in the lecture. So here are some videos. Let's see if this plays. Okay, so this is the autonomous execution. This is actually the policy trained on human demonstrations in simulation. And here it was just taught to like pick up this box and put it on the shelf. So as I mentioned, they have a recurrent LSTM policy, and they have multimodal outputs using a mixture of Gaussians. They also kind of coached their human demonstrators a little bit to intentionally make some mistakes just so they could illustrate some corrections. And that turns out to actually be kind of useful. So occasionally you'll see it actually make a mistake and fix itself. And this is the same thing running on a robot. This is not using vision for now. This is just using those AR markers to localize the object. So the training is all here in simulation, and then because they don't have to deal with perception, they could just do it on the real robot. And when you see the person actually pick up the box and move it, the policy is still running. So there's no kind of explicit reset. It just keeps running the RNN and keeps trying to do the task. And sometimes it makes a mistake, it screws up, but kind of repositions itself. So there you can see it doing something kind of sensible. All right. Here's the diagram from their paper of the architecture. So you can see over here there's the LSTM. This is to handle non-Markovian behavior. And at the top they're actually outputting a mixture of Gaussians. So that's this multivariate mixture of Gaussians box over here. And they call this the mixture density network, LSTM MDN. Their comparison looks at some of the different design choices for the network. So they look at a standard sort of what they call feed-forward MSE. This is a network that is not recurrent and outputs a unimodal Gaussian. So mean squared error is equivalent to log probability of a Gaussian. So this is just a unimodal Gaussian, and that never succeeds. If you have an LSTM with a unimodal distribution, that succeeds quite a bit on pick and place, but never on the second pushing task. If you have feed-forward multimodal, then it succeeds a bit more. And if you have both recurrent and multimodal, then that's the one that they found to work the best. So this is an evaluation of those two design choices, whether you use recurrence and whether you use multimodality. And then all their training was in the virtual world, but it still does something sensible in the physical world, but there's a little bit of a regression there. Okay, does anybody have any questions about this? Yes?
Why was this non-Markovian?
So the reason that the LSTM helps here, I suspect, is because just the human demonstrations are a bit inconsistent. Like you might move at a slightly different speed, maybe you accidentally let go of the joystick and the robot just stops, and then you resume. So there's all these decisions that humans make that are kind of arbitrary, partly due to not being perfectly optimal, and modeling those with a feed-forward network can be a bit harder. Yes?
How did they solve the multimodal problem?
So their network actually outputs the parameters of a mixture of Gaussians. So it outputs multiple means and multiple covariances, and then they take the sum of those Gaussians as the probability. Okay, so this one didn't use vision. There's a subsequent paper from the same group that does actually use vision. And the idea is very simple, very similar actually. Here they're actually doing everything in the real world, so they use a little game controller to pilot this robot to do a bunch of tasks. And now they're going to take their image and they're going to encode it with a convolutional neural network and then feed that to the LSTM. So this is now same idea but using images. Here's a video of this thing in action. One of the things I really like about this video is that this is like a very low-cost setup. So the robot is like $300. The game controller is about $100. So this is something that you know, a lot of people might be able to get to play around with this kind of stuff. So here you can see he's just demonstrating the behavior. This is the architecture of the network. So they use a ComNet to encode the image. They actually use an autoencoder to regularize the representation. So this is relating to the question that was asked before. And that's to handle the small amounts of data that they have. Small here is a relative term, so there's still a few hundred demonstrations per task. But you know, compared to like hundreds of hours of driving data, it's actually relatively small. And here you can see some of the stuff that this robot learned to do. So if you give it a little cloth and a little box of screwdrivers, it diligently tries to help you out by cleaning it off. And when it feels content with its job, it puts down the cloth and declares victory. And then as before, a person can come in and move the stuff around, and the robot will go and fetch it and try to do the task to its best ability. And the screen over there, this is showing the original image, I think, and this is the reconstruction from the autoencoder. This is just for regularization. Let's see some other tasks maybe. So here it has to find the little bubble wrap and put it on the plate. The robot has a pretty small payload, so that's why a lot of the objects are pretty light. But the cool thing here is that the policy is just still running, and the person goes in and messes with it a little bit, and it just sort of does its best to then attempt the task again. All right. Okay, some other things relating to imitation learning that might be good to know about. Imitation learning type methods, besides robotics and driving and things like that, they've actually proven to be quite popular in structured prediction tasks. So structured prediction tasks are tasks where your output is more structured than just a label. So a lot of natural language processing tasks fall into this category. If you're outputting a sentence, for example, for machine translation or question answering, you're solving a structured prediction problem. If you're outputting an image segmentation, basically a per pixel label in the image, that's a structured prediction problem. And the thing about structured prediction is that when you choose one part of the answer, that'll affect what is a good choice for another part of the answer. So if you have a question answering task, like someone asks you, where are you? And you're supposed to answer, I'm at work. If you output this word by word, if you have, let's say, an RNN that does this, if it says, I'm at work, that's all fine. But if it starts saying, I'm in, maybe the third word actually shouldn't be work. So even though this word is closer to what was in the data, this is not grammatically correct. So maybe if you output it in here, that should affect your choice of the third one. So maybe instead of saying, I'm in work, you should say, I'm in school or something. So in structured prediction problems, one part of the answer affects another part of the answer. And that looks an awful lot like a sequential decision-making problem. So in fact, a lot of these imitation learning algorithms for sequential decision-making have proven to be very popular in structured prediction because in structured prediction you typically have training data, so it looks like imitation learning, and there's a sequential component. Mohammed Narouzi is a researcher from Google Brain who, not in November, actually, yes, I think in November, actually. I'm trying to get him to come out here. We'll see if that works out. He might be in Toronto, but hopefully he'll come out and tell us about structure prediction, imitation learning, and RL. Another kind of domain that is kind of a popular one for imitation learning is interaction and active learning. So this is where you have to actually actively solicit feedback from people. And then another topic in imitation learning that we'll cover later on in the course is inverse reinforcement learning. So I alluded to this a little bit in the first lecture when I talked about inferring intentions. So far, all the imitation learning methods we've seen are kind of just blindly following the demonstration. They're not trying to figure out why the person is doing something. If you figure out why they're doing something, then maybe you can do a better job in new situations. So we'll talk about that later in the course. Okay. So what's the problem with imitation learning? Why is it not enough to just do imitation learning for everything and end the course today, basically? One of them is that we have an entire semester left, and you guys need to have grades. But the other one is that for imitation learning, humans need to provide data. And that data is typically finite. Like, even if you can get human drivers to drive for a whole lot, if the car is driving autonomously, maybe you can get it to drive even more. So even if humans can provide data through some relatively cheap mechanism, like the guy walking around on the forest trail, if you have an autonomous system that collect that data instead, maybe you can get even more data. So deep learning works best when data is plentiful, so that means that the more data you get, the better you'll generalize. And if your generalization is limited by how much you can get from the humans, that can be a bit limiting. Humans are also not good at providing some kinds of actions. So it's not too hard for a person to walk down a forest trail. It's not even all that hard for them with a little bit of practice to fly a drone or to drive a car. But if you imagine doing, let's say, a high-speed aerobatic maneuver with that drone, now it's a lot harder. Now the person has to actually figure out how the motors need to be actuated. That gets a little harder, not impossible, but harder. But now imagine a person, puppeteering a humanoid robot. Now you have to, just the engineering problem of getting a person to be able to pilot this thing gets really intense. And if you think of even more abstract things like the operations research style problems I mentioned in the first lecture, things like inventory management or finance, these might be things where you actually want to exceed the capability of the person by very large margins. It's just not enough to get human demonstration data. So the third one, and this is maybe more of an intellectual problem, which is that humans can learn autonomously. Humans imitate other humans, yes, but we can also learn things on our own. We're not limited to what we can imitate. So it seems like our machines ought to be able to do the same thing, and it's very unsatisfying if they don't. So they'll get unlimited data from their own experience, and they'll be able to continuously self-improve, which means that if they see mistakes, they'll be able to fix them. So it'd be awfully nice to go beyond imitation. In the 10 minutes I have left, I'm going to give a little preview of what's going to come next, and then we'll really dive into reinforcement learning on Wednesday. So if we want to go beyond imitation, one of the things we need to do is we need to define what it is that we want. So in defining what it is that we want, let's forget about the policy for a minute, and let's just think about writing down what we want if we don't have data. So what you want in this situation is you want to not get eaten by the tiger. This would be really nice. So perhaps a very reasonable thing to do is to say, well, let's minimize my log probability of getting eaten by the tiger conditional on my actions. And that's if you know what it means to get eaten by the tiger, this is a well-defined objective. You can optimize it, you can get a good policy or good actions. In general, what we would do is we would write down something like a cost or reward function. So we would say our probability of getting eaten by the tiger, in this case, that would be our cost, or the negative of our reward. So we would say, let's minimize the sum of this function c, which is the getting eaten by the tiger function, over all time steps. And of course, we don't get to choose which states we end up in, so the states are governed by some dynamics, but we get to choose the actions. So if we want to go beyond imitation learning, we need to define our objective in terms of a cost or reward function. So C for cost or R for reward. And a little aside, I mentioned before, states and actions popularized in dynamic programming by guys like Richard Bellman. That's also where the term reward function comes from. The term cost function, a bit more popular in optimal control. So if you see cost, don't worry, it's just the negative of the reward. And maybe a little bit of a cultural difference here. So Americans like to believe that life is full of rewards, and maybe Russians are a bit more pessimistic, so they think they'll incur costs. But the goal is the same. Okay, so costs and rewards in practice. Let's see some examples of some reward functions. These are some little benchmark tasks, some of which you'll see on your homeworks. Here's an example of a little benchmark simulation task that we often use in little reinforcement learning experiments. This is a robotic arm that has to grab this little ball and move it to this red spot. What might we choose to as our reward function here? Well, maybe we want something simple. Maybe we just say, let's have the reward be 1 if you do a good job, and 0 otherwise. Like that makes sense. You want something like pretty simple. Now, in practice, you'll often find that with the kind of reinforcement learning algorithms that we have today, these kinds of reward functions are very, very difficult to work with. And the reason they're very difficult to work with is because until you've moved that little ball to the target, you don't really know what you're supposed to be doing. So oftentimes when we go and solve these problems in practice, we'll end up with much more complex reward functions for doing this seemingly simple thing, like the standard benchmark reward function for this task actually looks more like this. Minimize the difference between the gripper and the object, so put the hand close to the object, minimize the difference between the object and the target, and also minimize the size of your action, so don't put like gigantic torques on the joints. And none of these are really things you want, but they're things that in practice are often necessary to get the kind of algorithms we have today to work well. So this is, sometimes people refer to this as reward shaping, although reward shaping also has another formal definition that's a little different from this. Another example, this little walking humanoid. This is something you guys actually will do for the first homework, although you'll first do it with imitation learning. So here it's a little guy with 2 legs and he has to run. So again, you might say, well, let's give him a 1 if he's running and a 0 otherwise. In practice, this again doesn't end up working all that well. So the kind of reward functions that might be used, there's like, some weight times the forward velocity, some other weight times an indicator for whether the torso is tilted away from the vertical. So if he starts falling, then you say, okay, this is bad, you should stop. And some reward for having the torso be above some height. So if you fall, you say, okay, that's not good either. And again, why do we need all this junk here? Well, because for the kind of reinforcement learning algorithms that we can plausibly build today, this kind of thing ends up being very hard to work with. And later on in the class, towards the end actually, we might have a lecture about exploration. And when we talk about exploration, we'll discuss these points a little bit more in detail. But I just wanted to show you guys this just to give you some idea of what kind of reward functions you might see. And if you look at like OpenAI Gym, for example, and you see these crazy reward functions, you'll know why. All right. Now, the last thing I want to mention is we talked about imitation learning, and then at the end I brought in this idea of reward and cost function. So can we actually write down a reward function for imitation learning? Like, does it correspond to some kind of well-defined reward? And it turns out that the answer is yes, that the reward for imitation learning, especially for things like the Dagger algorithm, is actually just the log probability of the action. So it is, in fact, a function of the state and action. It just says that the policy taken by the action taken by your policy in that state should match the expert's policy. And that's actually a well-defined reward. So that's actually the thing that Dagger is optimizing. When I mentioned before that Dagger has a bound, it's a bound on the difference between this reward and the optimal value of that reward. So this is the equivalent reward for imitation learning. Okay, this part, well, yeah, let me cover this. I have 5 minutes left. So what's the trouble with rewards and cost functions? I talked about this a little bit last week when I told you about how, well, in a lot of kind of simulated benchmark tasks like this video game agent, maybe you have a score that tells you how well you're doing, and that gives you a very natural notion of reward. The real world often doesn't expose a very natural notion of reward. So if you have this kid and the kid needs to pour a glass of water, if instead of having a kid there you want to have a robot, well, now that robot needs to figure out whether it's actually poured that glass of water successfully, and that might be a very difficult perception or computer vision problem in its own right. And this is something important to keep in mind, and we'll talk about some ways to mitigate that. But one of the things that might get you in a little bit of trouble if you don't consider this factor is that you can actually build an imitation learning or reinforcement learning, typically a reinforcement learning algorithm, that does handle really complex things like image observations, but then not be able to use it because you can't evaluate your reward functions from those observations. And here's like an example of something of an actual paper that has this kind of funny thing. So this is a very nice paper about actually transferring from simulation to the real world. But one of the issues they ran into is that, well, they have an algorithm for controlling a little robot arm using just raw image observations. And their main focus is on transferring from simulation to the real world, which they do successfully. But then in simulation, these are simulated images, they can localize this little red block that the robot needs to reach for just computationally because they know where it is in sim. But in the real world, they found that, well, we don't actually know exactly where this thing is. So let's actually code up a computer vision system to localize the red square. But then the trouble is that, Well, you say, okay, you're learning from pixels, but then you need to actually detect the thing just so that you can supervise the system so that it can learn to detect the thing. So that gets a little paradoxical. And this is maybe like a little bit of a cautionary tale in some ways, that if you're thinking of really rich expressive reinforcement learning algorithms, make sure that you don't neglect the reward function part of it, because you might actually solve the problem, but then not be able to demonstrate sort of how awesome that thing is without having to figure out an equally automated way to get the reward function. Okay, so more on this later. And the last thing I wanted to mention for today, this is the very last slide, a note about terminology. So starting on Wednesday, we're going to start talking about reinforcement learning. But one of the questions that might come up, and maybe already came up from last week, is like, well, what the heck is reinforcement learning? So the term reinforcement learning, at least in computer science, was in large part popularized by these guys, Andrew Bardo and Richard Sutton. And reinforcement learning seeks to solve these kinds of problems. So we already know what all these parts are, so I can actually just introduce this right now. You want to maximize your reward, subject to this constraint that your states are distributed according to your dynamics. And we'll get more into this on Wednesday. Now, this is actually exactly the problem that is addressed in optimal control and dynamic programming. It's exactly the same. So the problem statement in reinforcement learning, the problem statement in optimal control, and the problem statement in dynamic programming, it's the same problem. Sometimes when people say reinforcement learning, what they really mean is a particular class of reinforcement learning methods, which, if we want to get specific, we can refer to as model-free reinforcement learning methods. So those are methods that solve this problem up here without using this model. Now, using the model can mean one of two things. It means you know the model and you don't use it, or it means you don't know the model and you don't even try to learn it. So in both cases, you don't need the model. You can have model-based reinforcement learning, which again can mean one of two things. It means either you already know that model or you learn the model and then use it. So if you hear reinforcement learning and you're not sure what somebody means, well, they might actually just mean optimal control. They might mean this thing. Or they might mean model-free reinforcement learning or something in between. So yes, it's ambiguous. It basically means all of those things. And that's the answer. And just to conclude today's lecture, here's a picture of Richard Sutton being denied entry to the Deep Reinforcement Learning workshop because it was full. So those of you that had trouble getting to the lecture today or last week, for sympathy, here's a picture of the founder of this field having the same issue. All right, thank you very much. See you on Wednesday.
Questions.
Sure.
So how do we get the physics engine license?
We're going to send you that shortly. So all the enrolled students will actually get a license, but actually right now there's also a